Let's jump right into this explainer and look at the invisible, the catastrophic, and the totally slow motion challenges of aging dam infrastructure. Now, whether you're looking at a sleek arch dam that transfers all that massive water pressure laterally into the canyon walls, or a massive gravity dam that just holds the river back using pure immense weight, any engineer will tell you the exact same thing. A dam is really only as strong as the mountain it's anchored to. So let's unpack the anatomy of these incredible structures, look at how they stand up to the relentless forces of nature, and, find out why they sometimes fail.
To really understand dam integrity, we have to start by looking down, way down, into the unseen world right beneath the structure itself. Imagine this. How do you stop a 40,000-gallon-per-minute underground river? And no, that's not a hypothetical puzzle. It's a very real crisis scenario when you're building on karstic limestone terrain. That's a highly soluble rock that can literally dissolve and wash away, carving out massive underground rivers right beneath an existing dam. So the big question is, how do you battle a sudden, massive inflow like that without actually destroying the dam in the process? Just take a look at what happens when those erodible materials completely wash away. What we're seeing here is a massive, high-pressure conduit that's blown out right into the base of a quarry. And with the river nearby acting as an infinite source of water, pushing down with a driving head of over 300 feet, yeah, that is genuinely terrifying. Because when this phenomenon happens underneath a 70-year-old dam, you don't just have a leak on your hands. You've got a full-blown structural emergency that threatens the entire valley below. Now, to prevent those kinds of catastrophic blowouts, engineers use something called a grout curtain. Think of it as this invisible underground barrier of liquid concrete that gets pumped deep into the earth during construction. But here's the catch. Its effective life isn't infinite. Over decades, relentless hydrostatic pressure, which is the immense force of the water that actually increases linearly the deeper you go, can find tiny pockets of untreated rock, and it just slowly erodes it away until these dangerous channels open up. Okay, so that's the foundation, but what about the sudden explosive threats? Let's talk about overtopping and piping. What's truly wild about sudden dam failures is that they aren't just random, unpredictable mysteries. If you look at the data, the vast majority actually come down to just a few explosive categories, primarily overtopping and foundation defects. Usually, it's either a catastrophic failure of the mechanical pressure release systems, or it's the gradual internal defeat of the dam's core materials.
34%. That is a staggering number, and it makes overtopping the single leading cause of U.S. dam failures. This right here is the ultimate test of hydrological forecasting. I mean, can you accurately predict a 500-year flood? Because if a spillway, which is absolutely vital, it's the critical pressure release valve meant to safely discharge water carrying extreme kinetic energy at hundreds of kilometers per hour, if that spillway is inadequately designed or just blocked by debris, the dam is going to overtop. And sure, megadams are designed to withstand the probable maximum flood, but nature has a way of delivering black swan events that exceed all of our projections. Once water flows over the top of a dam, structural collapse is rapid, and it is inevitable.
Then you have another 20% of failures caused by something called piping, which is basically internal erosion. This happens when unfiltered seepage carries tiny soil particles away, forming these slow-motion sinkholes right through the earthen structure. And it's incredible to think about, but the total destruction of a massive impoundment can start with something as seemingly harmless as the roots of a tree or even a single animal burrow that gives that hydrostatic pressure a tiny path to escape.
And unfortunately, these rapid failures aren't just theoretical. The 1970s saw a tragic, closely spaced cluster of disasters. We're talking about everything from the Buffalo Creek Valley disaster to the spectacular billion-dollar failure of the Teton Dam in Idaho. These events wiped out property and, tragically, took hundreds of lives. But it was exactly this string of tragedies that finally served as a wake-up call, spurring the creation of the National Dam Safety Program that we heavily rely on to protect our communities today.
All right, let's shift gears from explosive collapses to something far more insidious, the slow burn of siltation.
If we contrast the sudden, terrifying violence of overtopping, we find the slow-motion failure of a dam's original design intent, siltation. You have to remember, dams are essentially massive sediment traps. Over decades, as a reservoir slowly fills with mud, its water storage capacity drastically shrinks. And this is a huge structural issue because it fundamentally alters the weight distribution against the dam itself, all while slowly choking off the water we rely on for irrigation, drinking, and the power grid. To really put the sheer scale of this engineering nightmare into perspective, the global cost of reservoir siltation is evaluated at anywhere from $15 to $20 billion. annually. We are literally losing massive chunks of our global water storage every single year. And if you look at high-head hydropower dams, even microscopic sediment particles containing quartz act exactly like industrial sandpaper, just relentlessly shredding massive metal turbines over time.
But here's the kicker.
The distribution of this threat is wildly uneven. A mere 10% of the world's river catchments generate the vast majority of the 40 billion cubic meters of sediment that are clogging up our reservoirs each year. If you happen to build a dam in one of these high-yield catchments, we're talking areas generating over 5,000 tons of sediment per square kilometer, well, siltation isn't just routine maintenance anymore. It's the primary factor dictating the absolute lifespan of your billion-dollar project.
So, how do engineers fight a creeping mountain of mud? They're forced to use extreme mechanical interventions. This can mean routing sediment-heavy floodwaters right through the reservoir, or even blasting massive bypass tunnels around the dam entirely. And when a reservoir is already totally choked out, operators have to resort to dredging or dry excavation, basically deploying entire fleets of machines to dig out millions of cubic meters of mud just to keep the lights on. It's this endless, incredibly costly war against geography.
Okay, but what happens when that invisible foundation threat we talked about earlier suddenly blows out? Let's look at crisis management.
When you've got a 40,000 gallon per minute leak erupting through a foundation, chaos is absolutely not an option. Engineers have to execute a strict, rapid-fire sequence of crisis management. You immediately appoint a dedicated manager and assemble an independent panel of experts. You aggressively investigate the site using fast drilling and geophysics to map that underground conduit, all while holding your breath and hoping your drilling doesn't accidentally shatter whatever is left of the foundation.
Now, standard concrete pumped into an underground river moving that fast would just immediately wash away. It would be completely useless. So, specialists turn to a pretty extreme solution. They pump boiling hot bitumen, we're talking over 200 degrees Celsius, deep underground, directly into the freezing, high-velocity river flow. The water aggressively cools the hot asphalt, causing it to congeal and forcefully create a massive, temporary plug right in the middle of the blowout.
And this is where it turns into a brilliant, high-stakes mechanical choreography. Because it's not just the bitumen. As that hot asphalt shrinks and cools in the freezing water, engineers are simultaneously injecting high and low-mobility cement grouts upstream. These grouts press hard against the cooling bitumen to create a permanent multi-material seal. It's literally an underground balancing act that requires continuous pumping until the river is completely choked off.
But sometimes all the extreme engineering in the world just isn't enough, which brings us to the ultimate resolution.
Sometimes, the math just makes the decision for us. Look at this ratio, 20-1. In states like Michigan, authorities have realized that thousands of smaller, aging dams no longer generate power or serve their original logging purposes. Removing a failing dam that has completely outlived its economic value can actually provide a return on investment exceeding 20-1 simply by eliminating the massive perpetual costs of just keeping the thing standing.
Instead of bleeding millions of taxpayer dollars to repair a valueless structure, tearing a dam down permanently eliminates the risk of a catastrophic blowout downstream. But it also does something pretty beautiful. It restores natural, flowing river habitats, it reconnects aquatic migration routes that might have been blocked for a century, and it revives the entire local ecosystem. Because sometimes, the absolute greatest engineering feat is simply knowing when to pack up your tools.
Which leaves us with a pretty provocative thought as we look toward the future. With over 2/3 of the nation's dams already aging past that critical 50-year mark, we are entering a totally new era of decision-making. We possess the extreme engineering tools, everything from massive bypass tunnels to pumping boiling bitumen, to save them. But as our built world ages and crumbles, we have to decide which of these concrete giants are truly worth fighting for, and which ones should we finally surrender back to nature. Thanks for joining me on this explainer. I have a feeling you're never going to look at a dam the same way again.